So next we're going to look at fast Fourier transform. Fast Fourier transform is an efficient way to calculate discrete Fourier transform. So it is not something that you use to find the spectral content of a signal, which is not discrete Fourier transform. It is discrete Fourier transform, but an efficient way to calculate discrete Fourier transform. It has a specific requirement, that is your data sample must be power of 2. So you can have 2 data samples, 4 data samples, 8, 16, 32, 64, and any power of 2, but you cannot have 5 data samples or 7 data samples or 10 data samples. Then you can not apply FFT. You have to apply the DFT formula that we have discussed. So this is the basic requirement of FFT, that your data sample must be a power of 2. Now, why FFT is efficient? That's a question, and we're gonna see the efficiency in the example. So it is efficient because of this, what you see over here. So when you are processing your calculations through a computer, basically the number of cycles depend upon how many complex multiplications do you have in general. So less number of complex multiplications that you have, that means your data will be processed fast. For n-point DFT, n-point means if you have 10 points, 16 point, I'm gonna do 2 to the power. So if you have 16 points, that cap n is 16. So for cap n point DFT, your complex multiplications are n square. So let's say you have 8 points. 8 square of course is 64. So you will have 64 maximum complex multiplications if you're using DFT formula through computers, right? Some of those complex multiplication, of course, you take power nk. So some of the power may be 0. So that complex number is going to become 1. But irrespective, if you're programming a computer, then of course that's computer's job to put those powers 0 and 1. But still, it is considered as one complex multiplication. That is, we are talking about w's of n and k. That's a complex number, right? So for an 8-point DFT, you will have 64 complex multiplication. For an 8-point FFT, if you calculate the discrete Fourier transform using the FFT algorithm, you will have n by 2 log 2n. That is 8 by 2 log to the base 10 of 8, right? 8 by 2 of course is, let me do it here, 8 by 2 is 4, and log to the 8 to the base 2 is 3. 2 to the power 3 is 8. So 12. You're gonna have 12 complex multiplication, 12 versus 64. Imagine if you have 2 to the power 15, 16 numbers in your data point. Then the complex multiplication, if you use DFT, is 2 to the power 15 is square. And if you use this, it's going to be 2 to the power 15 divided by 2 log to the base 2 of 2 to the power 15, which is going to be 15. So as the number of data point increases, FFT produce a very efficient way to calculate DFT. Now in MATLAB, the function that you use, the FFT function, if your number of data points are not power of 2, then FFT function is not going to use the FFT algorithm. It will just calculate, for example, if your data point of x, there are 10 data points, right? So 10 is of course not a power of 2. So it is just going to use the DFT algorithm and calculate the DFT of them. But if the data points are 16, 2 to the power 4, or any 2 to the power, then it's going to use FFT algorithm to calculate that. That's the difference. So if you have 10 data points or any number of data points that are not power of 2, how you can use FFT algorithm? So what we do is we add the number of zeros towards the end of the vector such that the total number of data points become a power of 2. So let's say your x is 1, 2 and 3. 3 samples. Of course, it's not a power 2. So basically, you can, for FFT formula, you go to the next power next power of 2, which will be 4, number of samples, which will be 4. So you can append a 0 at the end. This is called zero padding. Now zero padding does not insert any new information in your signal, because again it's 0. And when I say insert any new information, means it does not include any additional frequency in your signal. Remember, our goal is to find the frequency contents of the signal. When you do zero padding, it does not introduce any additional frequency in the signal. All it does is it is increasing, it will increase your time t0. Remember, you cut the signal to analyze for a specific time t0, and then you sample that signal, right? Now when you add zeros, basically you are extending that t0, because remember earlier your t0 had 3 points. You had 1, you had 2, you had 3, whatever. So now when you add 2, like a 0, 0, whatever, basically you are increasing the length of the input signal over which you are doing the FFT. Remember, the number of data points in your time domain is going to be the same number of data points in the frequency domain in one cycle of frequency. So if you are padding a 0 and making the total number of data points to be 4 instead of 3, in the frequency domain you will also have 4 data points. Sampling time is not going to change. So if you're sampling a signal by 8 kHz, it will still be sampled at 8 kHz. The only thing that you're changing is t0. So what will be the effect of t0 in the frequency domain? Remember, in the frequency domain, the total time of one cycle of samples is fs, right? Sampling frequency. That's one cycle. Now remember, ts did not change, so fs did not change. But t0 did change if you pad zeros. That means what is going to change? Frequency resolution is going to change. Again, you're not inserting more frequency, but you are interpolating between two frequencies. So you are basically fine-tuning the frequencies in this case, if you understand like that. So you're not going to introduce, if it's a cosine 2000 pi t, what is the frequency? 1000 hertz. So if you take 100 points, but you have to apply the FFT formula, then instead of 100 points, of course, the closest power of 2 is 128, 2 to the power 7. So you're going to insert 28 zeros towards the end. You're going to pad 28 zeros towards the end. Now that is not going to insert a frequency. It will still be 2000 hertz. But basically in the frequency domain, it is going to fine tune the frequency resolution. Why? Because you are changing the number of samples. So remember, delta f was what? Delta f is fs over n. Frequency resolution is fs over n. So although fs is the same, but n is changing. Instead of 100 points, you have 128 points. So your frequency resolution is going to become smaller. That is, you are interpolating the frequency. So that's the effect of using FFT, and how you can use FFT if you don't have the number of points which are power of 2. Okay. Alright, so let's move on and see what is the formula, or what is the derivation of FFT. So I'm discussing zero padding over here. Oh, by the way, if you're using FFT formula, then you don't have to physically go and add zeros. Let's say, if you're using 100 points and you have to use FFT, you have to add 28 zeros to 100 point input. You're not going to go and add zeros over there. All you need to do is FFT. Let's say x has 100 points, but you can just say x and then use 128 points. So what it is going to do, it is going to check the length of x, and then if it is 100, it's just going to insert 28 zeros and then give you the fast Fourier transform, the discrete Fourier transform using the fast Fourier transform algorithm. That's all you have to do. If you want to go and evaluate x using 256 point, you can do that as well. 256, right? It's going to insert how many? 156 zeros. It's going to pad 156 zeros if your length, input vector length is 100. But when you're using FFT, when I ask you any question and I ask you, hey, calculate the frequency resolution, if I give you, let's say, you have the 100 points, use the FFT formula, evaluate the signal, give me the frequency resolution. So what you're gonna do again, you're gonna say the closest number power of 2 is 128. That means 28 more points will be added into 100 points. Now the total length of the input vector becomes 128. So the frequency resolution is going to be fs over uppercase n. That's all you're gonna do. You're not gonna go up to 256 point. So go to the closest power of 2 when a question is asked. Now if it is being asked, that if I ask you use 1024 point FFT, then of course, irrespective of how many points are there in the original input signal, it can be 2 points only or 3 points. But if I ask you use 1024, then of course you're just gonna go ahead and do FFT x comma 1024. It's gonna create it's gonna calculate the DFT using FFT formula using 1024 point. That is going to pad bunch of zeros towards the end after the original data that you have. Okay, so remember that. Don't physically start putting that. If you're using FFT formula, just put down the number that you want after the input vector. So let's see, describe over here. All right, example 4.6, 920 points of a signal are collected through 8000 Hertz sampling rate. Determine the frequency resolution of the spectrum if DFT is used, that is the original formula of the DFT, and if FFT is used. So again, if DFT is used, you're not appending any zeros. 920 of course is not a power of 2, but you're just going to take the original number of points and divide the frequency resolution by that, not frequency resolution, sorry, frequency as the sampled frequency divided by the number of points, and that is going to be your frequency resolution. That is going to be the frequency difference between the two consecutive harmonics or two consecutive lines in the frequency domain. Now if FFT is used, the closest power of 2 to 920 is 1024. Do not go down. Make sure you have to go up because you have to append zeros. If you go down, then you're going to be removing some contents from the signal and you can lose the frequency. So make sure you do not remove the content from the signal. You always have to add zeros because adding zeros do not include any frequency contents. So if FFT is used, of course, 1024 minus 920, you're going to introduce 104 zeros. You're going to pad 104 zeros. And you have 1024 is 2 to the power 10. So you're going to just make it 2 to the power 10 and calculate the next, you're going to calculate the frequency spectrum 8000 over 1024, which is 7.8125. So again, frequency resolution is going to become smaller. That means you have now a better resolution to check your frequency contents. Okay, so let's move on. So FFT, there are about 4 different techniques to perform FFT. I think there are 2 of them given in your book: decimation in frequency and decimation in time. I'm just going to discuss decimation in frequency. Once again, most of the work that you're going to do is using MATLAB FFT formula. So this is just to show you how one of the FFT algorithm works. What are the things that are involved in that algorithm, and as long as you understand those things, it's good enough for this course. Again, when I'm going to give you a voice signal or something else, you will just be using the FFT formula to find the frequency spectrum and to change the frequency spectrum when we use filters and all those things. So frequency, decimation in frequency and decimation in time, these two are also called radix 2 FFT algorithms. So I'm going to discuss decimation in frequency. We will start with DFT formula. This is the DFT formula that you use to do your homework and everything else that you did last week. So x of k, remember k is the frequency content, and k again go from 0 to cap n minus 1. Remember again, frequency spectrum is a periodic, is periodic in nature. And we know the formula, summation from 0 to n minus 1, all the samples of x, input samples, that is twiddle factor wn kn, and again twiddle factor is e to the power negative j 2 pi n. So basically this thing is e to the power negative j 2 pi n k over cap n, right? And out of that, twiddle factor is e to the power negative j 2 pi over n. Why? Because this is constant. As long as you are not changing the input number of samples, n cap n is constant. However, when you're taking the summation, your lowercase n will be changing, and of course which spectral content you are calculating, that k is going to be a variable as well from 0 to n minus 1. So the only thing that is constant is e to the power negative j 2 pi over n, so that's called twiddle factor, and we can calculate that for any number of samples, and once we have that, we can replace it over here. Let's say if it comes out to be 1 minus j2 twiddle factor, let's say, just an example, right? So you can just replace this by 1 minus j2 n k, right? And of course if you're using MATLAB, as I said, you don't really have to do all that. But if I ask you, or if I ask you, show your work. Show your work means that you're going to calculate twiddle factor clearly. And then if I give you 5 points, then you have to show me. You don't have to show me all the multiplication or addition. All I'm asking you is to show how to expand this expression. You can show me only what is the value of twiddle factor. You don't have to go and put the value each and every time. All you have to do is show me, let's say, x of 0 plus x of 1, w's of, let's say, power 1, x of 2, w's power 2, so on and so forth, right? And then at one point you can just show me what is w, let's say 1 minus j2, so you show me on top that w is 1 minus j2. You don't have to repeat that over here. And then of course I already know what is the vector x. So basically when I ask you show me the work, this is basically what I'm trying to ask you, just to understand, just to see actually that you have the understanding of how to expand this expression. That's my basic idea or goal, is that you need to have understanding of different variables that are involved over here, k, lowercase k, lowercase n, uppercase n minus 1, and how to expand the summation. So that's what my goal is. Now you can still go and calculate w's of 1, w's of 2 using your calculator, using MATLAB, and then plug in the value. You don't really have to show me the value when you're plugging it in, and then just give me the result. That's okay. But this expansion I'm expecting from you if I ask you to show me the work. Okay. All right. So right here, basically this expression, and so you're gonna show that for x of 1, you're gonna show that for x of 2. So basically you're gonna change the value of k over here, value of k over here, and so on and so forth. So what we are going to do with the DFT expression. Now remember, in this case, number of samples are power of 2, right? That means k is also power of 2. So what we're going to do, we're going to divide this expression into 2 halves. We're gonna divide this expression into 2 halves and write each half separately. So we're gonna start x0, x1, w total factor to the power k, plus whatever we have, and we're gonna go up to 1 point before the half one, right? So x n by 2 minus 1, twiddle factor k n by 2 minus 1. Remember k n, right? So this is my n, n by 2 minus 1. That's my n. Over here n is 1, right? K times 1. And then the next value in the sequence is going to be x n by 2 w's of k n by 2. Again, this is my n right here. And then it's going to go all the way to n minus 1. This is the last value of lowercase n. Last value of lowercase n. So we wrote down the expression such that I have the first half here, and then I have the second half of the expression here clearly written. Okay, so let's move on. So now, since I have broken the expression down into two halves, what I'm going to do, I'm going to write each half with its own summation. So the first half, the summation goes from 0 to n by 2 minus 1, right? 0 to n by 2 minus 1, which is the value of lowercase n. So n goes from lowercase n goes from 0 to n to minus 1, n by 2 minus 1, xn, wn, kn, which is DFT. And then the second summation goes from the next value n by 2 to the last value n minus 1. And again, this is the same. Okay, so far so good. Now we're gonna go ahead and modify the second term, this term. And how are we gonna modify this second term? Observe. Instead of going for the summation from cap n by 2 to n minus 1, I want to keep the summation to be the same. N is equal to 0 to n by 2 minus 1. N is equal to 0 to n by 2 minus 1. And if I do that, basically what I'm going to do over here in the argument of x of n, remember the first value of this was supposed to be cap n by 2. So what I'm going to do here, I'm going to add cap n by 2 over here. So when n lowercase n is 0, it's going to start at x of cap n by 2. And then when it will go to n by 2 minus 1, so when you replace n by 2 minus 1, then it is going to be n by 2 plus n by 2, that is n, and then n minus 1. So it's going to go to the upper value n minus 1. Get it? So I change the summation value, and again over here where I have the lowercase n, I change that n by n plus n by 2. So here n plus n by 2, so that I can write down w's of kn, right? And then w's of kn by 2, w's of n, k times n by 2. So I basically distribute it, because this is my w, this n and times k, right? So I distributed that w's of n, n of k, w's of n by 2 times k, right? So this is w's of n by 2 times k on this. So I did that. Okay, so w's of n to the power cap n by 2. Now remember, w's of n is e to the power negative j 2 pi over cap n, right? So when I take the power of that to cap n by 2, what I'm going to get? E to the power negative j pi. And e to the power negative j pi, remember, using Euler's identity, cosine pi minus j sine of pi. Sine of pi is 0, cosine pi is negative 1. So that's going to give you negative 1. So I'm going to go ahead and replace this thing by negative 1 to the power k, because the power of k is there, remember. Okay, so the same sequence. Now because my summation is the same, so I carry that summation out of the parentheses, and I have x of n from the first one plus negative 1 to the power k, which is negative 1, w's of n to the power cap n by 2, that's negative 1, and of course we have the power k, times x of n plus 2, which is here, and both are multiplied by the total factor to the power kn. So the total factor times kn. So I get this expression 4.38. Okay, now if I say my k is 2m for any value of m usually go from, or m not usually, m always go from 0, 1, 2 all the way up to n by 2. N by 2 minus 1, sorry. N by 2 minus 1. So if I say k is 2m, that means I'm evaluating the even number component, because if my m is 0, that's going to be x of 0, my m is 1, it's going to be x of 2, m is 2, x of 4, and remember n is what? N is total number of terms, which is power of 2. So let's say it's 16, so 16 by 2, 8, 8 minus 1, 7. So you put m is equal to 7, that's going to be 14th, right? So these will be all even number component. Let me just make sure that I'm pretty sure m is, yeah, m is, it goes to n by 2 minus 1, yeah. Okay. So for my even number component, again I'm going to use this formula, but for even number, my power of k, negative 1 to the power of k, for even powers is going to be 1, right? So negative 1 to the power 0, negative 1 to the power 2, all of those values will be positive 1. So I'm going to replace, I'm going to eliminate that and just put a positive over here. So this is my basically even number component. These are my even number components. Okay, let's move on. For my odd number components, odd component, I'm gonna choose 2m plus 1. Again, m goes from 0 to n by 2 minus 1. So now for odd number, of course, the power of negative 1 to the any odd power k, that's going to be negative 1. So I'm going to go ahead and replace this positive by negative and write this down, right? Now let me go back. Where is it? Okay, so we are using this expression right here. Okay, now when we have w's of n, this, observe we have two terms over here, but basically it is the expansion, because k is 2m plus 1, remember, right? So w's of n, k is 2m plus 1 times n. So you have w's of n, 2m times n, which is this, and then w's of n, n to the power n, which is this, right? That's why these two terms are here. Okay, just wanted to explain that. Okay, let's move on. So if you look at w's of n square using, again, that's going to be e to the power negative j 2 pi over n square, which will be e to the power negative j 2 pi over n by 2, right? I'm going to take this 2 and I'm going to put it at the bottom. It's the same thing, right? So I'm going to call this w's of n square, I'm going to call this w's of n by 2, which is basically, it goes with whatever you have over here in the bottom of e to the power negative j 2 pi. So I'm going to call w's of n square as w's of n by 2. So if we go x of 2m right here, x of 2m, I have w's of n 2mn. Of course, k was 2m here, right? So w's of n 2mn, that means w's of n mn square. So I can write this down as w's of n by 2 mn, right? w's of n by 2 mn, and I'm calling x n plus x n plus n by 2, where n goes from 0 to n by 2 minus 1. I'm calling this as a variable a of n. So my even number component is basically a DFT of an, with n by 2 points, right? N by 2 point. This is n by 2, n goes from 0 to n by 2 minus 1. So total number of points are n by 2. So even component is basically DFT of a of n with n by 2 points. And likewise, odd number components goes from n is equal to 0 to n by 2 minus 1, again this formula right here, this one. And then b's of n is this right here, this is b's of n, w's of n to the power n, which is this, and then again this thing is gonna be w's of n by 2 to the power mn, like we discussed over here. So this is again DFT of this, the whole thing, bn w's of nn with n by 2 points, So this becomes your sample now, and you are taking the DFT of this sample with the n by 2 point DFT. And again this is an and bn, and goes from here, and goes from 0 to n by 2 minus 1, 0 to n by 2 minus 1 right here. So basically DFT of x of n with n points with the frequency in decimation FFT algorithm, it becomes DFT of an with n by 2 points and DFT of bn total factor to the power n with n by 2 points. That's what frequency in decimation algorithm comes down to. Now of course the natural question is going to be, okay, this is all good, where's the efficiency? So let's look at that. First let's look at example 4.7. Determine the spectrum of this sequence using the FFT algorithm, and again the sequence is 3127 and it has 2 to the power 2, right, 4. So we don't have to pad any zeros. All we need to do is, this is actually we have to do with both DFT and FFT, and it's going to show you actually the savings. So first we use the DFT formula, the usual formula, which is the one that we discussed. This is the formula 0 to n minus 1. N minus 1 of course in this case is 3, right, because total number of sample is 4, so n is equal to 4 here. Total number of samples are 4. So 0 to n minus 1, x of n total factor to the to the base n to the power nk. So I expanded this to show that what will be x of k. X of 0, w's of n, and so first is n is equal to 0, so we put n is equal to 0 here, n is equal to 0 here, then n is equal to 1, n is equal to 1 here, n is equal to 1 here, n is equal to 2, 2, n is equal to 3 and 3, okay? And then we calculated the value of total factor, e to the power negative j 2 pi over 4, cap n is 4, which will be e to the power negative j pi over 2 cosine pi over 2 minus j sine pi over 2. Cosine pi over 2 is 0, and then sine pi over 2 is 1, so negative j1. So total factor came out to be negative j1. So look at this table. Now wherever you have the total factor, you're just going to go ahead and plug in negative j1 and then take the power, whatever power is that. So the first is 0, second is 1, 2, 3, when k is equal to 0. So 0 and k is equal to 0, so all of them are 0 actually in this case. N is 0, here n is 1, so it's going to be 0, 1, it's going to be 0, 2, it's going to be 0 times 3, right? So anyways, it's going to become 0. So that means it is only the x0 plus x1 plus x2 plus x3, which is 30. And we did this exercise before. In the second one, x of 1, k is equal to 1. So you're going to go k, n, k, 0 times 1, then n is 1, k is 1, k is 2, n is 2, k is 1, and n is 3, k is 1. Right? I'm not showing the multiplication because 2 times 1 is 2, of course. And likewise, x of 2, n is 0, k is 2, k is 2, n is 1 here, k is 2, and n is 2 here, so 2 times 2, 4, and k is 2, and n is 3 here. 2 times 3 is 6, so negative 3, and likewise go for the fourth one. So you have how many maximum? You have 16 maximum complex multiplication. 1, 2, 3, 4 in each row, so total 16. Now observe, of course, some of them are power 0, which will be 1. Irrespective of that, you have 16 complex multiplications here, right? Now if you go to FFT, So we apply FFT. Again, we have to calculate the even number factors and odd number factors separately, right? So we have an xn plus x of n plus n by 2 and bn xn minus x of n by 2. So we first calculated the values of an and bn. N goes from 0 to n by 2 minus 1. So remember, n over here is 4, n by 2 minus 1 is 2 minus 1, 1. So basically n here is 0 and 1, two values. So n is 0 and 1. So you calculated a naught, n is equal to 0, x0 plus x of n by 2. And then you calculated a1, x of 1 plus x of 1 plus n by 2. Remember, n by 2 is 2. So x of 1 plus x of 3, that's a1. And x of 0 plus x of 2 is a naught, right here. And likewise, you calculated b naught and b1 by subtracting x of n and by subtracting x of n plus n by 2 from x of n. So once you have a naught and b, a and b, a n and b, remember, even number components are the DFT of an with n by 2 points, and odd number components is the DFT of bn times the total factor to the power n with n by 2 points. So now you go over here, this table. So first I calculated the two total factors, total factor n by 2 and total factor to the base n, cap n. So one is coming out to be -1 and the other is -j1. So x of 2m, which is the even number components, when I calculated it, I have, you can go through it, of course, look at the formula carefully. So you have total factor, this total factor, to the power m times n, right? So m times 0, m times 1. Remember, m also goes from 0, 1. 2 times 0, the first even number component, x of 0, and 2 times 1, the second even number component, x of 2, right? So m is 0 and 1, which is the same thing as lowercase n, which goes from 0 to n by 2 minus 1, right, over here. Okay, so I expanded the formula, this formula right here. I expanded this for this equation, for this data set. So now when you go ahead and use m is equal to 0, all you have to do is put m is equal to 0 over here, m is equal to 0 over here, right? And then when m is equal to 1, then you're going to put m is equal to 1 here and m is equal to 1 here, and then a naught and a1 are here. So right now here you can see there is no complex multiplication whatsoever. You go and calculate the odd number component. Again, I went ahead and I expanded this formula right here for m is equal to 0 and m is equal to 1, right? You can see the expansion over here. So when we do that, the first, when m is equal to 0, that's 2m plus 1, so 2 times 0 plus 1. So the first component is going to give you x of 1, the odd number, first odd number component. And that's going to be 1 complex multiplication, 2 complex multiplications over here. And the result is 1 plus j6. And likewise for x of 3, when m is equal to 1, you have 2 complex multiplications right here. So total are 4 complex multiplication versus how many? 16 complex multiplication for the DFT formula. So again, right here, total n by 2 log of n to the base 2. That is 2 times 2, 4 complex multiplication versus 16. So that's the efficiency. And this is the technique, this is the method that you're using for FFT algorithm using frequency decimation method, decimation in frequency method. So if I ask you, use the FFT algorithm, decimation in frequency, which is the only algorithm we are studying right now. So if I even ask you, show me the work using FFT algorithm, you are using decimation in frequency, remember that. All right. If I don't ask you, you are free to use MATLAB. All right, let's move on to example 4.8. You have a signal 4 cosine 6000 pi t, 10 cosine 8000 pi t, sampled at 5 kilohertz. All right, so look at the frequency first. This has the frequency 3 kilohertz. This is a 3 kilohertz component, and this is the 4 kilohertz component. So you have 3 kilohertz and 4 kilohertz component in the signal. Sampling at 5 kHz, what does that mean? It is undersampled because Nyquist rate is 8000, twice the amount of the highest frequency. So Nyquist rate is 8000, it is sampled at 5000, it is undersampled. That means you can expect the aliasing noise in the sample. And you at what frequencies? So sampling at 5 kHz, 5 minus 4, 1. You can expect aliasing noise at 1 kHz, and 5 minus 3, 2. So at 1 kHz and 3 and 2 kHz, you can expect the aliasing noise here. All right. So I'm asking, I'm saying that 100 samples. I'm calculating. I'm getting 100 sample, and I'm asking you to use the FFT algorithm to calculate the spectrum and determine the frequency resolution, of course. And I'm also asking you to treat the data using what window function? Hanning window. Also treat the data using Hanning window function, and then observe the spectrum again. All right. So first, your frequency resolution. Now the closest power of 200 is 128 2 to the power 7. So using that, using padding 128 zeros, we're gonna get delta F, Fs over 128, that. Okay. And this is all I explained which components are going to be there. Aliasing frequencies will be here. These are the original component. Now, if the signal is sampled with the frequency more than the Nyquist rate, that is, if it is sampled oversampled, then all the frequencies in the signal will be less than or equal to Fs by 2. If it is critically sampled, then it can go up to Fs by 2, but if it is oversampled, all the input frequencies can come up to Fs by 2. Why? Because again, you are oversampling, mean that your sampling frequency is twice the highest frequency of the input signal, right? That means if your sampling rate is 4 kHz and it is oversampled, that means the highest frequency has to be less than 2 kHz in the signal. So between 0 and Fs by 2, which is the folding frequency, you can see all the input frequencies. And that's what we've been discussing. All you have to do is to go from 0 to Fs by 2 if it is oversampled. Now this signal is undersampled at 5 kHz. So you will not see all the frequencies from 0 to Fs by 2, that is 0 to 2.5 kHz. You will not see all those frequencies. Why? Because 0 to 2.5 kHz, you have a frequency component 3 kHz, you have a frequency component 4 kHz, they are outside 2.5 kHz. So you're not going to see those frequencies if you just look from 0 to Fs by 2, because again it is undersampled. So as long as the signal is oversampled, you can guarantee that all the frequencies will be from 0 to Fs by 2, folding frequency or Nyquist frequency, not the Nyquist rate, Nyquist frequency. But if it is undersampled, there's no guarantee, right? That's not the guarantee. So you can forget about that. You will still plot the signal frequency spectrum from 0 to Fs. So your range will be 0 to 5 kHz for the spectrum. You are calculating 128 points. And observe that all these frequencies, they are less than 5 kHz. So you know that from 0 to Fs, you will be able to see all these frequencies. Even before you plot it, you can figure that out. So let's go ahead and now plot it. Here you go. I use the FFT function, and we plotted the amplitude spectrum of both signals, right? Amplitude spectrum, remember, is what? X of k, which is the magnitude of x of k, divided by total number of points. That's the amplitude spectrum, double-sided. Okay, so now observe the x-axis is in hertz. So I'm going from 0 to Fs, 0 to 5000 hertz. So this is last point is 5000 hertz. So observe the frequency. You have 4000 component, you have 3000 component. Those are the original frequencies in the original signal. And observe 2000 component and 1000 component. That's the aliasing noise. So it's very consistent with our theory, what we learned. Observe so much spectral leakage. So much spectral leakage. So I'm going to use the window function and observe all the spectral leakage pretty much is minimized. You still have those components, aliasing noise components, and you still have the input frequency component, but the aliasing, but the spectral leakage is minimized. That's the last example.